these notes as we go in case that you want to go back and look at these afterwards. I also posted a couple videos in the note section for today of other people talking about this same subject. Some people in the past have found them helpful. Some people have not because other people go kind of fast through some of the stuff. But I figured that if you watched my video once or twice and you're still not fully understanding, maybe seeing it from somebody else's perspective might help you out a little bit. All right, so balancing equations is what we're going to go over today. So the notes that we're going to go through today are right here. And then there's 2 YouTube videos that I talked about that go over the same thing in a little bit different detail. All right, balancing chemical equation. It's all about making sure that we have equal amounts, balanced amounts of atoms on either side of our chemical equation. So you may remember from Tuesday, I talked about chemical reactions and how we start off with the reactants. So our reactants are our starting material that react together. And then those make our products. So the substances that are produced, the ending material of our chemical reaction, we call that the products. So we start off with the reactants on one side of the equation. And then we have this big arrow here, which it's sort of similar to like an equal sign in a math equation. And then we have the products are on the other side of the equation. They are our final results. So we're changing one set of substances into something new, something different. So one of the big things that I talked about yesterday is how chemical reactions rearrange the atoms that we're dealing with, right? And so, it looks like my labels on here got a little bit messed up. Well, we looked at this photosynthesis equation yesterday. We have carbon dioxide and water that is absorbing energy from the sunlight. So does anybody remember what type of reaction we call it when it absorbs energy?
Endothermic?
Hey, nailed it, Kayla. Correct, endothermic. So photosynthesis absorbs sunlight energy in order to do the reaction. So it is an endothermic reaction. And our products are glucose, which is this big molecule right here, and oxygen. So one of the main things that I talked about yesterday is that we have the same types of atom on each side, right? On our reactant side, we have some H's, we have some O's right here and here, and we have some C's. And our product side, we also have some H's, we have some O's right here and here, and we have some C's. So we have the same types of atoms on either side. C's, H's, and O's on the reactant side. C's, H's, and O's on the product side. All we're doing is switching around where those atoms are going. We're switching around how those atoms are bonded to each other. So instead of these H's being bonded to these O's, instead now they become bonded to these C's and O's over here. And then the other O's are kind of left on their own. So we're moving around our atoms, we're switching them around, we're rearranging them, but we are not adding anything new or getting rid of anything, right? There's no nitrogen or phosphorus or aluminum over here on the product side. because there wasn't any of that in the reactant side to start with. Similarly, we have C's, O's, and H's in the reactant side. So that means we cannot have just C's and H's or just H's and O's on the product side. We have to have all three different types that we started with. We're just rearranging them, moving them around. So we call, when they're in a big written out form like this, where we have the reactants on one side that are being kind of added together, and then the arrow, and then some products on the other side, we call that a chemical equation. So instead of writing out carbon dioxide plus water makes glucose and oxygen, instead we write down the chemical symbols for those substances. CO2 plus H2O gives us C6H12O6 plus O2. That's a basic chemical equation. So there are a couple different parts to these chemical equations that is going to be really, really important for you guys to keep track of. The first one, the obvious one, is the chemical symbols, right? Those C's, H's, and O's from before. But you may have noticed there's also a couple numbers that are mixed in with those guys. One of those numbers is called the coefficients. So the coefficients represent how many of each substance that you have. And you can find the coefficient because it'll be the big number that is before or in front of each chemical symbol. So on our photosynthesis equation right here, we have three different coefficients. There's this 6 right here, there's this 6 right here, and there is this 6 right here. These guys are coefficients. They're big numbers in front of each of these chemicals. And what they're doing is telling us how many of each chemical there are. So it's telling us that we have 6 carbon dioxide compounds, 6 water compounds, and 6 O2 elements. When there isn't a coefficient in front of the compound or atom or whatever it is, then it's kind of like there's an invisible number 1 right there. So if there isn't any big coefficient number, then we just assume that that means that there's 1 molecule of glucose. So 6 carbon dioxides and 6 waters turn into 1 glucose and 6 oxygens, 6 O2s. So these big numbers here are the coefficients. There's also these little numbers down here. They are called the subscripts. Oh, so here we go. So there's the coefficients up here with these big arrows. And then these little numbers are the subscripts. They're telling us essentially how many of each atom are in a certain compound. So for example, water has 2 hydrogens and 1 oxygen. Carbon dioxide has 1 carbon and 2 oxygens. Glucose has 6 carbons, 12 hydrogens, and 6 oxygens. So the important thing to remember about subscripts is that they cannot change. They cannot be altered in a chemical equation. Pretend that they are like permanent marker set in stone written down here. All right, these coefficients we can change around a little bit to make things balanced, and we'll talk about how we do that in just a second. But these little subscripts down here, they are permanent. They are stuck like that. We cannot touch them at all. It's illegal. It's not allowed. You can't do it. So the subscripts are permanent. They're set in stone. But the coefficients are changeable. We're allowed to change them into different numbers in order to make it a more balanced equation. And like I said, exactly how we do that, we'll get to in just a second here. So coefficients, big numbers in front of our compounds, in front of our molecules, subscripts, little numbers down here at the bottom. Coefficients, we can change, we can edit them to be different if we need them to be. Subscripts, we cannot. They are permanent. They are set in stone. We can't change them any way whatsoever. Only these big coefficient numbers out here. So before I move on to how we go through balancing an equation, does anybody have any questions so far about chemical equations, coefficients, subscripts? Any questions?
On the big number, I can pick up any number or just 6.
So they can't. Good question. They can be any number. And the photosynthesis example, it just so happens that they are all 6. But in different examples that we'll do in a little bit, you'll see that these coefficients can be different numbers. Some of them might be like a 2. Some could be a 4 or a 3. Some of them, there aren't going to be change. We're just going to leave it with no coefficient because we only need the one molecule. But correct, they do not all have to be 6 all the time. They can, the coefficients can be different. It just depends on the chemical equation you're working with. All right, great question, Dwee. Thanks for helping me point that out. Any other questions about any of these equations before we get into actually balancing them?
So just to make sure, the subscripts can't change. They have to stay the way they are. We don't change them at all.
They have to stay the way they are. So however you're first given them, however they're first written out, that's the way that they have to be at the end.
So all the 6s stay the same?
So these 6s could potentially be changed because these are the coefficients out here. But like this 6 right here and this 6 right here, they will always be the same. We can't change these 6s down here.
All right,
All right, great questions, guys. So those are the different parts that go into a chemical equation. Usually, when scientists first figure out what type of chemicals are reacting together, they don't know at first exactly how many of each atom are going to be part of the equation, part of the reaction. So that is where balancing chemical equations come in. So usually, when we're going to balance chemical equations, we're going to start off with just the compounds themselves: CO2, H2O, O2, glucose, those things. And then it's up to the scientist to figure out what coefficients can go in there to make sure we have the same number of each atom on the reactant side and on the product side. So the way that we'll kind of go through the steps that we're going to go through is we'll start off with a written out chemical equation. Sometimes you'll have to write them out when you're like doing them later on. But in this class, we start off with the chemical equation. The first thing that we're going to do is check for what's called atom balance, meaning that we're going to see how many C's, how many H's, and how many O's are on the left-hand side, the reactant side, and how many C's, H's, and O's are on the product side. Our goal is to make it so that there's the same number of C's, the same number of H's, and the same number of O's on the reactants and product side of the equation. Or depending on the equation, it might be other atoms, but that's the basic idea. Each type of atom, you should have the same amount on either side. If we start off with an unbalanced equation, we'll change some of the coefficients, try to balance it out the best that we can. We'll then recheck how many atoms that we have on either side and see if we successfully balanced the equation. If we didn't, then we have to go back in and change around the coefficients a little bit more in order to make that balancing happen. So it's kind of hard to explain just in words. So we're going to go through a couple examples and I'll kind of show you exactly what I mean by all of this. So here we have a basic chemical equation. HgO, mercury oxide, is going through a chemical reaction and becoming mercury and oxygen, O2, on its own. So this guy is getting separated out into two different pieces. So we have to make sure that we have the same numbers of Hg's and the same numbers of O's on either side of the equation. So initially what I like to do is write out the different atoms that we have. So in this case, we have Hg mercury atoms and O oxygen atoms on either side. And then check for atom balance, meaning that we're going to see how many of each atom do we have on the reactant side and how many do we have on the product side. So if we look over here at our HgO compound on the reactant side, we have one Hg atom and one oxygen atom. All right, good start. Move over here. We have one Hg atoms. So our Hg's are balanced. We have one on either side. So that's nice. But we have two oxygen atoms on the right-hand side here. O2 means that there's two oxygen atoms that are bonded together. So our equation is unbalanced. We have one oxygen on the reactant side, two oxygens on the product side. That's no good. That's an unbalanced equation. So we're going to try and fix it. We're going to try and make this equation balanced. So we have one Hg on either side, one O on the reactant side, but two O's on the product side. So because this O is a 1 and this O is a 2, that makes this equation unbalanced. We don't have the same number of oxygens on either side. So the next thing that we can do is try to adjust some of our coefficients and see if we can make our oxygens balance. So what I'm going to try and do is change this coefficient over here into a 2. So right now there's not a coefficient there, which is similar to having it just be like one single one. But what if I make this a 2? Make the coefficient over here a 2. So now we have two HgO compounds. There's like one HgO and two HgO that we just added. The cool thing about the coefficient is that it applies to both atoms in the compound. So since the Hg and the O are bonded together, since they're a compound together, this 2 goes to this Hg as well as to this O.
Mr. S, could you have added any other number? Does it have to be a 2? I mean, how did you get
It doesn't. Nope, it
just...
could have been any other number, but I probably should have said that. My thinking is that we have 2 oxygens over on this side. So if I make it so that we have 2 oxygens over on this side, maybe I can make this equation balance out. So if I want this O to be a 2, I have to put a 2 in front here. So luckily, this now gives me 2 O's on the reactant side, so that's good. But unfortunately, since this 2 is here, I also have 2 H's, 2 Hg's as well. So now our oxygens are balanced. I have 2 O's on the product side, and thanks to this guy, I have 2 O's on the reactant side. So that's good. We completed that step. But, now I have 2 Hg's on the reactant side. So I balanced my O's, but I made my Hg's unbalanced in the process. So sometimes this happens. Actually, a lot of times this happens. When you go to balance one thing, it'll cause something else to become unbalanced. So now the trick is going to be try to figure out, well, if I have 2 Hg's on this side, I can't take away this 2 because I need it for the O's. And I can't do anything with the 2 on this O because this is a subscript, right? And we're not allowed to touch those. It's illegal. It's against the laws of chemistry to mess with this subscript. So what if I do something to make it so that instead of just 1 Hg, I have 2 Hg's on the product side? Luckily, that is pretty easy to do. If I just add a 2 Hg over here, now I have 2 Hg's on my reactant side and 2 Hg's on my product side. So this is looking good. We may have made it to a balanced equation. Let's double check. So the first thing we'll check is the number of Hg's. I have 2 Hg's on the reactant side and 2 Hg's on the product side. So those are balanced. I have 2 O's on the reactant side and 2 O's on the product side. So those are balanced as well. So since the Hg's are balanced and the O's are balanced, now we have a fully balanced chemical equation. We have 2 Hg's and 2 O's on the reactants and the product side. So our final answer, if you will, our final equation is 2 HgO yields 2 Hg plus O2. So this is our final complete balanced chemical equation. We started off without these coefficients. We added the first one to try and balance the O's. Since that unbalanced our H's, we had to go in and add the second one in order to balance the Hg's. So as we go through balancing these equations, we're going to constantly be checking, okay, I made this change. Is this one balanced? Yes. Did we cause something else to be unbalanced? If so, how can we go back to the balanced form? What can we do with these coefficients? Because remember, these are the only things that we can change. So like Dewey was asking earlier, it doesn't have to be any particular number, or like Araceli was asking, if 2 made it balanced, or if 6 made it balanced, or if 3 made it balanced, whatever helps to balance the equation, that is the coefficient that we can use. So a couple more things that I wanted to bring up before I ask for any questions, because I'm sure people have some, because this is a little bit tricky. So sometimes you'll have to put a coefficient in front of an element with a subscript. So that little number on the bottom. When you do that, when a coefficient and a subscript interact, they multiply. So for example, if we had to do something with those O2s in our other equation, like put a 3 in front of them, 3 O2s means we do 3 times 2, and that gives us 6 total oxygen atoms. If we have something with multiple atoms, like H2O, water, so this 4 down here, sorry that this little thing pops up to hide it. I still have not figured out a way to make it not appear. But if we have 4 H2O, that means that we have 4 times 2 is 8 H's, and then 4 goes with the oxygen, which doesn't have a subscript, so there's no multiplying. So we just have 4 O's but 8 H's. 4 times the 2 by the H gives us 8 H's in water, if that is our coefficient. So if a coefficient and a subscript are in the same chemical, you multiply coefficient times subscript. This is something that's definitely going to come up later on, so I just wanted to make sure that we were ready for it now. All right, so I'll go back to this screen. So we are going to do some more examples of this, I promise. But does anybody have any questions at the moment? Anything that I did with our HGs and Os that you were super confused about or just totally did not understand? Alrighty, sounds like everybody is kind of, sort of okay with some of this so far. So what I'm actually going to do is do some examples from you guys that are going to come straight off of the homework that I posted today. So as a treat for you guys for being here in person to this Zoom call, we're going to work on some of these homework questions together. So on the homework, it's kind of set up like this, where you have some blank areas to write in coefficients that you need to, and you can keep track of your atom number in these little spaces down below. So what I'm actually going to do is stop presenting there and bring up a whiteboard to work on. Okay. All right, here we go. So our first one, O2CaO. We have calcium, Ca, and oxygen, O2, create calcium oxide. So we have 2 different atoms in this chemical equation. All right, we have calcium and we have oxygen. So the first thing that I like to do is figure out how many of each atom do we have on each side. So over on our reactance side, so over here on the left is the reactant side, and then over here is our product side. So on the reactant side, how many calcium atoms do we have?
I think 2.
So we have our calcium right here. And does this guy have any coefficients or any subscripts with it?
Calcium.
No.
We have 2 calcium.
So to start off with, we only have 1 calcium to start. So in this guy, the Ca is just on its own. That means that we're starting off with 1 calcium atom. What about oxygen? How many oxygens are we starting with?
1. No,
2.
2, because we got our little subscript down here. So we're starting off with a total of 1 calcium and 2 oxygens over on our reactant side. What about over here on the product side? How many calciums do we have?
1.
1.
1, precisely. And then how many oxygens?
1.
1, exactly. So we have 1 calcium and 1 oxygen atom that are bonded together to make a compound called calcium oxide. So, good start. 1 calcium, 2 oxygens on the reactant side, 1 calcium and 1 oxygen on the product side. So, obviously, this is not a balanced chemical reaction. We have 1 and 1 calcium, so that's good. Those are balanced to start off with. We have 2 oxygens on the reactant side and 1 oxygen on the product side. So these guys are not equal. They're not balanced, so we do not have a balanced chemical equation to start off with here. So I'm thinking that if we have 2 oxygens already on the reactant side, maybe we can somehow get 2 oxygens on the product side. So what can we do with this compound up here that get 2 oxygens?
I think we put number 2 on later oxygen.
So we can put a number 2 here in the front in the coefficient spot. So now we have 2 oxygens. So yay, that's good. We have balanced our oxygens, hooray. But we don't just have 2 oxygens. We also have 2 calciums because 2 goes to both of these guys equally. So while we have 2 oxygens, and that's good, we now also have 2 calciums, and that's not good. So our equation is still unbalanced. We still do not have, now our oxygens are balanced and equal, so that's nice. But our calciums are not. We have 1 calcium over on the reactant side, but 2 calciums on the product side. So it's not equal, we are not yet balanced. So what can we do with calcium over on the reactant side to help balance out our calcium numbers?
Put a 2 before it.
Put a 2. Bingo, bango, bongo. So now we have 2 calciums over here on the reactants. All right, so now let's check if this is a balanced equation. We have 2 calciums on the reactant side and 2 calciums on the product side. So that is equal and balanced. We have 2 oxygens on the reactant side and 2 oxygens on the product side. So that is equal and balanced. So now we have a balanced chemical equation. 2Ca plus O2 produces 2CaO. That is our final answer, our final chemical equation. So we started off by counting how many atoms of each type were on each side. We then tried to balance the oxygens. That caused our calciums to become unbalanced. So we came back to the reactant side, tried to balance the calciums, and that did end up balancing our entire equation. All right, anybody have any questions about this example? Anything that I did or we talked about that you're not quite sure why or doesn't quite make sense yet?
Can we have another example?
Of course. So let's see, what is our next problem here? N2H2NH3. Ooh, this is a good one. Okay. So we've got some nitrogen, N2. We've got some hydrogen, H2. And when those guys react together, they produce NH3. So our starting equation is N2 plus H2 produces NH3. So what are the 2 different atoms that we're working with in this example?
The N and H?
N and H, precisely. So we've got some N's and we've got some H's. So if we start over here on the reactant side, how many N's do we have over here?
2.
2, precisely. How many H's?
2.
Also 2. 2 N's and 2 H's. What about over on our products side? How many N's do we have over here?
3.
3.
Huh? How many N's do we have?
1.
1.
1, precisely. So we have
yes, yes.
1 N. But how many H's do we have?
So
3.
H is 3?
3.
H is 3, precisely. So this is like a single NH3 molecule. So it's 1 N and 3 H's that are all bonded together. They're making probably covalent bonds with each other. So NH3 has 1 N and 3 H's. All right, so this is obviously a very unbalanced chemical equation. We have 2 N's on the reactant side, but only 1 on the product side. We have 2 H's on the reactant side, and we've got 3 on the product side. So this is quite unbalanced. So on these ones, where it's kind of hard to figure out which one to start off with first, I usually like to start looking at the ones that have the smaller overall numbers. So N is 2 and 1. H is 2 and 3. So N's overall are smaller. So I think that'll be a good place to start with our balancing. So we have 2 N's on the reactant side and 1 on the product side. obviously we can't do anything about these two over here. This is a subscript and we're not allowed to touch those. So we have to do something over on the product side in order to make the ends balance. So what can we put in front of NH3 to make these ends balanced?
2.
A 2,
No.
precisely. So if we put this 2 here, now we have, instead of one N, we have 2 N's on the product side. So that's good. That seems like a good start. These guys are the same number now, which is always a plus. But now we've also changed our H's. So how many H's do we now have on the product side?
A 3.
We started off with 3. But what happens when we have a coefficient and a subscript that interact with each other?
You multiply 2
Multiply.
times 3, 6.
Yeah, multiply.
Oh,
So-
6.
2 times 3 is 6. Exactly. Ooh, that's a weird 6. But anyways, all right. So when we put this 2 here to make 2 NH3 molecules, we now have 2 N's, and 2 times 3 is 6 H's. So our N's are balanced. So that's nice. That's a step in the right direction. Our H's, though, are pretty unbalanced. So we have 6 H's over on the product side. I don't really want to mess with this number anymore if we don't have to, since our N's are nice and balanced. So is there anything we could do on the reactant side to make there be 6 H's?
We put 3 on H.
Ooh, I like that idea.
Yeah.
So if this guy becomes a funky looking 3, now 3 times 2 is 6.
6.
Ooh, this looks nice. All right, so let's double
Oh.
check here.
I understand now. When we do something like that, and we need to do n equal to n, reactant need to equal to product, like n equal to n and h equal to h.
Right, and so now that we did all this balancing, we have 2 N's on the reactant still. That didn't change. But we have 2 N's on the products, which means that 2 and 2 are the same. So this is now nice and balanced. These guys are equal to each other. We have 3 times 2 is 6 H's on the reactant side. And 2 times 3 is 6 H's on the product side. So now these guys are also equal to each other. So they are balanced. So now we know we have a totally balanced chemical equation. 2 N's on the reactants and 2 N's on the products, 6 H's on the reactants and 6 H's on the products. Both of those numbers are the same on each side, so we are balanced. So our final equation is N2 plus 3H2 produces 2NH3. All right. Very nice work, everybody. Any questions about this example before we move on to another example? Anything that we did here that you're still a little confused about or not sure of?
No, Mr. S, no.
Nah.
All right. Well, it definitely sounds like you guys are starting to get the hang of it. And so we'll do 1 or 2 more examples to kind of really bring everything home. Let's see. Oh, this is a good one. Coming up. U2O plus C. C, U2 plus C. Leave some space. All right, ramping up the difficulty a little bit because now we've got 3 atoms going on. So our starting equation is Cu2O, which is, Cu is copper. So we have copper oxide, Cu2O, plus C gives us Cu plus, I'm going to fix this plus because it looks crappy, Cu plus CO2. So first things first, what are the 3 different atoms that we are dealing with?
CU, O's, and C's.
Correct. So we've got Cu is one of them. O. Ooh, hello. Hello. Oh, there you go. Okay. Froze for a little bit. O is our second one. And C is our third. All right. Next up is figure out the initial number of atoms. So over on the reactant side, how many Cus are we starting?
2.
2, precisely. 2 coppers. What about how many O's?
1.
Precisely. 1 O right here. And then how many C's?
1.
1. Exactly. 1 C right here. Perfect, perfect. Very nice. All right. On our product side, how many Cus?
1.
Correct. How many C's?
1.
Mm-hmm. And how many O's?
2.
Exactly. 1 Cu, 1 C, 2 O's. So 2, 1, 1 on the reactant side, 1, 2, 1 on the product side. This is not a balanced reaction. Something here is incorrect. So our carbons are already balanced. So maybe we're not going to have to mess with those. So we can leave them alone for right now. Our Cus and our Os are both kind of equally unbalanced. So since Cu is first, let's go ahead and try to balance Cu first. So we have 2 Cus on our reactant side and 1 Cu on our product side. So what can we do in order to make these balance?
Bring the CU2 to the CU1 or vice versa.
Add a 2 in front of the CU on the product side.
Production. Yeah.
There we go. That is a little bit more clear. All right, yes. Add a 2 to the Cu on the product side. I think that should help things nicely. So now this guy just goes with Cu right here. So now we've got 2 CUs on the reactant side and 2 CUs on the product side. All right, so that helped balance that out. That was a pretty good start. So let's move on to oxygen. We've got 2 oxygens on the product side, 1 on the reactant side. So what can we do to balance our oxygens?
We need to put 2 on reactant.
Exactly. So this 2 is a subscript, so we can't mess with this O2 at all. So all we can do is change this guy. So we can put a 2 on our reactant right here. So now that did help us balance our O's. So we've got 2 O's on the reactant side now. That's good. But what happens when we put...
Now we put 2 on the reactant. We need to multiply Cu, and we got 4 Cu on reactant.
Exactly.
And we need to change Cu on production.
Is down here. Now we have 2 times 2, like Dewey was saying, we got to multiply. When we have a coefficient and a subscript, we've got to multiply. So 2 times 2 gives us 4 CUs on the reactant side. So we balanced our O's, good, but now our CUs are unbalanced, not
equal to. We need to change Cu from product again.
Yep, I would probably, because again, we can't mess with this oxygen at all because this is a subscript and we can't do that. And this guy has to be a 4 because it has the 2 times 2. So instead of trying to fix it over here, can we just go over to our CUs over here and maybe change this coefficient into something different?
Yes. We change it 4.
Hey, I like that idea. So 2, as it turns out, is not the best coefficient to go there, but that's okay. We can always change coefficients, right? We can always go back and change them if we need to. So if we make this instead a 4, now we have 4, and then this becomes a 4 as well. So let's do our final check. 2 times 2 is 4 CUs on the reactants and 4 CUs on the products. So these are equal. 2 O's on the reactant side and 2 O's on the product side. These guys didn't get at all. So these are equal. And then the C's didn't even do anything to them. 1 C on the reactant, 1 C on the product. So these guys are and always have been equal. So now we have a fully balanced chemical equation. 4 C's on both sides, 4 CUs, 4 coppers, 2 oxygens, and 1 carbon on each side of the chemical equation. So our final answer here is 2 Cu2O plus C produces 4 Cu plus CO2. So that is the final balanced form of our chemical equation. All right. Anybody have any questions on this example? Again, anything that we did that you're still a little bit confused about or you're not really understanding where some of these numbers came from?
I understood now. In the morning, I check your assignment and I don't understand everything. Now I know what am I gonna do?
Yeah, this one especially, if you don't have somebody do some examples for you, it's really tricky.
Yes.
and figure out. All right, so you guys seem like you are doing pretty well on here. So I'm going to give you one kind of complex example to see if you can work your way through it with me a little bit. So if we have some CO2 plus H2O produces C6H12O6 plus O2. So, getting a little bit bigger now. Does anybody recognize this reaction?
Yes.
Do you remember what it is, Dwee?
So long.
That's okay. It's kind of a tricky name. Other people, if you catch on to it in a little bit, feel free to chime in and say what you think it is. So, as always, even though it's a bigger, more complex equation, we're going to do the exact same steps. So first off, what are the different atoms that we're dealing with here?
CO.
Yeah, H.
We got some O's. And what else do we have?
H.
H. So we've got some C's, O's, and H's on both sides. So on our reactant side, how many C's do we have?
1.
One C. This one is tricky. How many O's do we have on our reactant side?
2.
Close. We have 2 O's right here.
And 1 O on H2O.
So how many
And
total O's do we have?
3.
3, exactly. So when you get some larger chemical equations, this will happen. They'll be the same atom in different places, but you have to count it all together. So on the reactant side, we have a total of 1, 2, 3 O's. Very good. And then finally, how many H's on the reactant?
We have 2 H.
2. Precisely. All right, let's come over here. Now on this product side, how many total C's do we have?
6.
And how many H's do we have?
12.
And how many total O's do we have?
H. 6. H.
8, exactly. 6 O's right here and 2 O's right here. Whew. Those are some big numbers that we are dealing with. But that's okay. We'll take it one step at a time and kind of see how everything shakes out. So let's see here. We have 1 and 6, 3 and 8, 2 and 12. I'm going to go with my favorite strategy, which is to start with the smaller numbers and see if we can balance those first. So we have C is the smallest numbers. There's 1 and 6, which is a lot smaller than these guys down here. So if we have 6 C's over on our product side, what can we do on our reactant side to get the C's to balance?
Part 3 on CO2.
So if we put a 3 here, how many C's will we have?
Oh, just 3. Oh, I think about 6.
Ah, there we go.
Yeah,
So yeah,
but
we count the C and the O separately when we're putting in our coefficients right here. So if we put 6 C's right here, then now we have 6 C's on our reactant side. However, we have also now changed our total number of O's. So now we have 6 times 2 O's right here, plus 1 over here. So how many total O's do we now have on the reactant side?
12, 13.
13, exactly. So we have 6 times 2 is 12, plus the 1 still over here gives us 13 O's. All right, so now our C's are balanced. Our O's and H's are still kind of a mess. So I'm going to continue on with my strategy of trying to balance the smaller numbers first. Now, there's a lot more O's, so I'm going to kind of skip that one for now and go to our H's. 2 and 12 H's is smaller than 13 and 8 O's. So we have 12 H's over here on our product side, and we have 2 H's, this little H2 right here, on our reactant side. So is there any way that we could change our reactant H's to equal our products?
Put a 6.
But this
6, I like that idea. So now we have 6 times 2 is 12 H's on our reactant side. The
we
6
add this.
still affects this O right here. So now we have to look at the total number of O's. We have 6 times 2 is 12, plus 6 more over here is 12,
16.
6. I think 18, right? Are other people getting 18? I think it's 18. Right? Yeah, 6 times 2 is 12, plus now there's 6 over here. So yeah, 18. Oh my goodness, what the heck is that? That's a tiny bit better, I guess. So we now have 12 H's on this side, and we made this guy a 6. So we have a total of 18 O's on our reactant side. So our carbons are balanced and our hydrogens are balanced. So all that's left to remain is to balance our oxygens over on the product side. So we have 18 oxygens over here. We have 8 oxygens over here, and they're split between these 6 right here and these 2 right here. So these 6 oxygens we're probably not going to mess with, right? Because our carbons and our hydrogens are already balanced, and so we don't really want to go around messing with this number if we don't have to.
Yeah. If we put the number on this, we need to do everything again.
Exactly. And I don't want to do that if we don't have to.
Yes.
These 6 oxygens are going to kind of stay as they are, I think. But these oxygens is a lot easier to mess around with because we have just the oxygens themselves to deal with. So we need 18 oxygens, right? That's the magic number we're looking for to get balanced. We already have 6 that we said we're not going to mess with because we don't want to mess with this. So we need, besides these 6, in order to get up to 18, we need 12 more oxygens. So what can we do over here to give us 12 oxygens?
We put it on products.
Ooh. I think you're onto something here, Dewey.
Yeah.
So if we put 6 here, 6 times 2 is 12. And 12 oxygens right here, plus the 6 that we have right here, gives us 18 total oxygens. 12 plus 6 is 18. So let's do our final check. 6 C's on the reactant side and 6 C's on the product side. That is equal 18 O's. 6 times 2 is 12, plus 6 is 18. On the reactant side, 6 plus 6 times 2 is 12. 6 and 12 is 18 on the product side. Those are balanced. 6 times 2 is 12 hydrogens on the reactant side and 12 hydrogens on the product side. These are balanced. And now we have our final equation, which some of you hopefully have recognized as our photosynthesis equation that we were looking at earlier this week and earlier today. Six CO2 plus 6 H2O produces C6H12O6 plus 6 O2. That is our final equation and our final, or the correct equation for photosynthesis, the way that plants take carbon dioxide and water and turn it into sugar and oxygen. All right, so look at that. You just took that big giant equation and made all of the 3 different atoms balance out on it. Very, very nice. Very good job. All right, so does anybody have any final balancing equation questions? Anything that we did with this photosynthesis equation that you totally got lost on or you got super confused about?
Only the last one. I got so lost. I'm sorry.
That is okay. Unfortunately, we only have a couple minutes left, so I can't go.
I wrote down everything as you was going, so I kind of got the same thing you got right there. So I'm just keep on looking and thinking, and go back out the first ones I looked at, and going. I get it understood, and if I don't, the next meeting I ask you about it.
Cool, perfect. And you can also always go back and watch this video and watch me go through it again.
Oh yeah. Okay, great.
On the classroom, for sure. All right. So speaking of the classroom, let me see if I can go back. Oh man, I can't switch that easily. So for the daily assignment for today, like I said, we actually have already as a class gone through the first 3 questions. There we go. So all you need to do is go back in and fill out what are the coefficients and what were our final numbers for each type of atom. You can either go back and work through them on your own, or go back and watch me go through them and kind of fill it out as you go along. I did leave one final equation for you guys to work on your own. And so take some time, look at it, go through all the steps that we were just doing, figure out, this one, it already tells you the atoms that are here. So you just have to figure out how many are we starting with, and then how can we adjust these coefficients right here in order to make sure that all of the atoms get balanced on either side of the equation.
Oh my goodness. I don't know we have anything under bottom, and I just do 3 questions and I turn in that.
That's okay. You can go back and fill in the 4th one and resubmit it if you need to.
Yeah, thank you.
All right, and then I think the assignment for tomorrow is just a simple question having to do with like the coefficients and chemical equations. So it should be a little bit easier and pretty easy to do for a Friday assignment. And I think we have literally run up to the very end of our class today.
Can you return my assignment today, because I want to do something
Yeah.
at the bottom. In the
Sure.
morning I didn't say everything.
Yeah, that one's kind of hiding out down there. So
Okay,
yeah,
Mr. S, thank
Do
you.
that.
Have a good one.
no problem. So if you guys ever do have questions about anything, you can always send